Hello and welcome. This is chapter 15. This video will be over sections 1 and 2. First section is pretty short, so I'm just going to combine it with section 2. And this chapter is all about oscillations. Oscillations is such an important type of motion that it has an entire chapter devoted to it. And hopefully by the end of the chapter, you will be at least convinced, or I can show you the arguments for why oscillation might be one of the most fundamental type of motion that we observe. Although we don't see it every day, it's all around us. The sound that we hear, the light that we see, the vibrations in the molecules that make up the solids that we have, all of it comes from things oscillating. Temperature coming off of objects is something from oscillations at its microscopic level. But we certainly start with some basic ideas, especially from the main systems, mechanical systems with which we've been working, the pendulum and the oscillator, or this mass on a spring. So what is oscillatory motion? It's any time the motion repeats itself. Certainly a sine wave is possible, but also this sawtooth wave is possible. The fact that this motion repeats itself every so often, that first of all, that's called a period. And we have the so-called frequency of oscillation. We define these basic kinematic variables of frequency and period. Frequency is the how many times per second that a system repeats its motion. The period is that time interval where the motion is different before it returns to its initial state. So oscillatory motion in general can be any type of motion as long as it eventually repeats itself. It turns out, however, that the most important type of motion from which all the other ones are based is simple harmonic motion. And simple harmonic motion, well modeled by a mass on a spring, is an example of actual sinusoidal repetition of the motion. And so sinusoidal motion is the basic one, and these first couple sections deal with the kinematics of, that is the mathematics of the motion of oscillation, and also the connection that simple harmonic motion has with uniform circular motion. So again, we have this figure, the air track glider. Those aren't as common anymore, but it's certainly a possibility. In the physics lab, we have springs or masses with wheels that move on tracks, and that's another way to produce this motion. Okay. Let's look at the derivatives of a motion diagram. So if we record position versus time for a object in simple harmonic motion, right, it'll start further out at a point called the amplitude. The packet, well, the largest distance from the equilibrium point that the oscillator can travel is called its amplitude. So capital A is amplitude, and we can look at the position graph and obviously relate it to the acceleration graph. So we see at the very beginning, when I release it from rest, its velocity is 0. And so you see on the position graph that the slope of the position graph is 0, which perfectly aligns with the 0 value of the velocity. Now on this dotted line, the particle, or on this dashed line, is when the particle has been released from rest, increases speed until it flies through the center at its maximum, and then slows back down to rest before coming back. Once again, after it's slowed down at rest, the velocity has been 0. Velocity is 0. So every point, the position graph, the slope of that line is the actual value of the velocity graph. You see in the middle here, between the starting point and that dashed line, the velocity reaches a minimum, which means the velocity through that point on the position graph is a maximum, or not a maximum, but the largest negative value that it can have. And then sure enough, it turns around, and then the velocity has the largest positive value that it has as it's going through there. And so this process repeats itself, and you see that what I'm talking about on this other picture here. This is a graph of position and velocity versus time. So these peak to peak widths are called the period. They're not the wavelength. If you've heard of the wavelength before, that's in a different context, but these peak-to-peak widths are the period. Same object. And so we have a couple equations here. This is the equation of the position versus time for an object in simple harmonic motion. We have the amplitude times the cosine of this new quantity called omega times t. Okay, so this is sinusoidal motion. Omega is now called angular frequency. In previous chapters, it's introduced in chapter 4 as angular velocity, and it takes on a slightly different role in chapter 15 because the thing's not rotating, it's oscillating. And so when we're talking about an object in circular motion, it rotates with an angular velocity, but when we're talking about an object that's oscillating back and forth, it oscillates with an angular frequency. And we use the same symbol, and they're actually somewhat related, as we're going to see in the next section. But we define angular frequency in a couple different ways. In terms of the period, it's 2 pi over t. It's kind of hard to see, but the angular frequency is 2 pi over the period. It has units technically of radians per second, just like angular velocity does. It's actually more helpful to see that it's directly proportional with frequency. Angular frequency is theoretically a little bit more important, but obviously period and frequency are related as F equals 1 over t. Angular frequency, period t, and frequency f all contain the exact same amount of information, no more, no less. Different contexts will lend themselves to which one you use. For instance, when we're describing the motion, of the object with an equation, omega tends to be the one that we use. If there's an object that's rotating very rapidly, we might use frequency. For instance, in the voltage that's oscillating in the electrical outlet on your wall, that is oscillating with a frequency of 60 hertz. So 60 times per second, the voltage goes to a maximum and then 0 and then a minimum back to 0. Period might be useful when we're dealing with systems that take a very slow time to oscillate. You go to museums, you see very, very long pendula. Interestingly enough, those pendula, not only do they swing back and forth, but their period is so long that the motion starts to curve as it's spinning to show that the Earth is rotating. That's called a Foucault pendulum. We have one actually at Exploration Place in downtown Wichita. And so the maximum speed, if we know that the position is a times cosine of omega t, we can take the derivative of that value to get omega times a sine of omega t. And this certainly goes through the chain rule and all the things from calculus, but the maximum speed of a object in simple harmonic motion is the angular frequency times its amplitude. Now that might seem kind of weird because if you remember from circular motion, the tangential velocity of a particle in uniform circular motion was equal to omega times r. And so this should look a little bit at least plausible, omega times a. The issue is that we don't actually reach the top speed on the edges of oscillation. In fact, that sine function tells us that it's actually 0 on the edges, but that speed is actually reached in the middle. So this formula looks like tangential velocity v equals omega r, but again, it takes slightly different context. And here's the big connection between uniform circular motion and simple harmonic motion. Okay, so it's helpful perhaps to think about a different example first. If you have a particle that is moving in a circle, if you shine light directly above it, you would see that its shadow made simple harmonic motion on the floor. Okay, and so the what we call the projection of the particle moving in a circle, if that undergoes simple harmonic motion, then you take this problem, turn it back around and say, well, if a particle is undergoing, if a physical particle is undergoing simple harmonic motion, is there some way we can relate it to the backwards version of that? Like, is there something that is moving in a circle? Right, and then indeed they have this example of a ball that's moving and it matches perfectly with the angular, with the oscillation of the mass on a spring. You have to be, to do experiments like this, has to be very close and careful, but that's the big idea, is that a particle moving in a circle will have some sort of relationship between its oscillation counterpart. And there'll be many opportunities to understand that. So the angle that's being swept out in the circle is called the phase. And the phase is the thing that is rotating at angular velocity omega. And the cosine of the phase times the amplitude tells us the actual position of the particle. So this is a picture that I would make sure that you spend a lot of time studying to convince yourself of how uniform circular motion is related to it. So the phase is the phase of the oscillation is the angle from, say, some reference point on the horizontal axis that an imaginary vector has that's rotating at angular velocity v, making this a system oscillate with angular frequency omega. That's what a phase is. Phase constants have to do with where we start off, because where we start off will affect the graph that we get, but it's really the same graph that's just flipped, not flipped, but translated left or right, depending on the phase constant that we use. So if the phase constant is 0, for instance, that means we release the object from the very far right. If the phase constant is, say, pi/2, then it's released from the center. But you have to be careful, because the phase constant of minus pi/2 would be that it's released from the center as well. But those differing angles, one that's plus and one that's minus, give different information about the initial velocity of the particle. So if you look at the function of velocity down here, if you have an extra pi/2 here, if at t equals 0, if sine is plus pi/2, then the velocity is negative. That means it's moving to the left. And if at time t equals 0, if the phase constant is minus pi/2, then it's moving to the right. And actually, you can generalize that and say that if the phase is in the upper hemisphere of this phasor diagram, then the particle is moving to the left. If it's in the lower hemisphere of this phasor diagram, then it's moving to the right. Phasor diagram is a terminology that we use later when we're studying AC circuits, but that's exactly what this is. It's a vector that's rotating in this kind of abstract space, for which the horizontal component gives us the actual position. And so this is a good practice with different phase constants and the different pictures to look at. So this is definitely worth studying in the PowerPoints. For instance, this first one, if you have a phase constant of pi/3, that means it's moving to the left, and it's at amplitude of 1/2 a. These pictures are really good. If the phase constant is minus pi/3, it's at the same location but moving right. And this is the types of things that I was talking about earlier. A phase constant of at t equals 0, phase constant of pi means it's all the way to the left. And it even shows you examples of these graphs. So the phase constant is typically new to most folks, but the connections about circular motion and simple harmonic motion is the big takeaway in these first couple sections. So again, to recap, a system that oscillates repeats itself in a time equal to the period, which is 1 over the frequency, which is also related to the angular frequency. Those three terms mean the same thing. And we can describe the change in the quantity of interest as a cosine of angular frequency times time plus a phase constant. So that's the beginning of the start of this chapter. In later chapters or in later sections, we'll talk about energy, and we'll use forces and torques to derive how mechanical systems oscillate. And then in the later chapter, in the later sections of this chapter, we will certainly talk about more realistic systems where objects can run down and actually stop even when they're oscillating, or even when you can ramp up their motion by applying an external force. That's it for these first two sections. Thanks for your time, and we'll see you back here for the next one. Take care.